Hello everybody, and welcome back to another CIV 398 assignment tutorial. So in this tutorial, we're going to be covering question 3 of assignment 3, and this is a really good question to know how to do because it's a standard midterm question. I almost guaranteed you're going to get something like this because if we look at it, all we do is give you position functions, x1, x2, and x3. And look at all the stuff we can ask. We can ask for the deformation gradient, the displacement gradient, as well as characteristics of the deformation. So this is why it's such a juicy midterm question, is because we give you so little, but can ask for so much. So question 3 itself says, consider the motion, and it gives us, again, 3 position functions. We're given x1, x2, and x3. And the question wants to determine 4 different things. The first one is the deformation gradient, and the second one is the displacement gradient. So notice how I said the deformation gradient F and the displacement gradient nabla U. Now the chances of F and nabla U appearing in the midterm are very, very small. So you guys are going to have to remember what exactly the deformation gradient is, as well as the displacement gradient. So again, the deformation gradient, that's F. The displacement gradient, that's nabla U. How do I remember them? Well, I remember that displacement functions are U1, U2, and U3. So therefore, the displacement gradient is nabla U. So they both have U in it. That's just how I remember it. Then the question asks us in part C and part D to determine some characteristics of the deformation. So part C asks, is the deformation physically possible? While part D asks, is the deformation characterized by expansion, contraction, volume preservation, or none of the above? So a lot of you guys may be asking, what is none of the above option? Well, that's the case if the deformation is physically impossible. So if we get it's impossible, we answer none of the above. However, if the deformation is physically possible, it'll either be expansion, contraction, or volume preservation. So we're going to have to keep a lookout for that. So the first part of the question says, what is the deformation gradient? So again, this is F right here. And we remember that we can determine F by just simply taking a bunch of partial derivatives. And F in particular is the partial derivatives of x1, x2, and x3. And if we look at our question, we're given x1, x2, and x3. So all we have to do to determine F, or the components of F, is we need to take the partial derivatives of x1, x2, and x3. It's a big X1, big X2, and big X3. So I covered how to do this in the assignment 2 video, and you guys should know it's not as bad as it looks. I know it looks disgusting. I know it looks gross. I know you look at this and say, you know what, I give up on this class. This is too complex. But again, it was actually really, really simple. But I know for a lot of you guys, you're going to say, Clayton, I know it's simple, but I still don't want to do it. Well, luckily for you guys, there is a Mathematica command for partial derivatives, which is actually just derivatives in this case, and that is D and then square brackets and then 2 inputs. So the first input, which I just put as x, this is going to be our position function. So this would be x1 is equal to, let's say, 3x4 plus blah, 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 blah. And then the second input is what we want to differentiate to. So let's say that we input x1 and we want to differentiate that to big X2. Well, in this spot right here, I'd put big X2. So what I recommend for you guys is you guys can use this as more of a check. I wouldn't use it to try and calculate all the derivatives. It gets, well, let's be honest. You guys will be quicker doing this by hand than you will be inputting it into Mathematica. Now, of course, if you guys really want and you guys want to nerd out, then you guys can create a Mathematica function that'll give us F in terms of the position vector X, but that kind of defeats the purpose. I didn't give you guys that because I want you guys to understand exactly where F comes from. Because again, if you guys know exactly how to calculate F, it's easier to do it by hand than it is to throw it into Mathematica. I'd recommend just using Mathematica as a check and nothing more. So this is the deformation gradient F, which is part A. But then part B says, okay, what is the displacement gradient, nabla U? And if we look at the definition in nabla U, it's the exact same formulations as F. The only difference is we're using U1, U2, and U3 rather than X1, X2, and X3. So you're saying, okay, well, I don't have U1. What do I do? Well, we remember that we can actually determine U if we're given X. So if we want to, we can use this relationship above, below where X is equal to big X plus U to determine U. Now the problem with this is two major problems. The first one is we're going to have to find U1, U2, and U3. That right there by itself is a lot of work. But even after we find U1, U2, and U3, we're going to have to take the partial differentials of all those, which is again even more work. So there must be a nice, easier way because this above is quite tedious. It can be time consuming and just a real pain in the ass. Well, we can remember that there is actually a relationship between the two gradients, and that is this. F is equal to the identity matrix I plus nabla U. So let's say that we have F, which we do from part A, and we want to solve for nabla U. Well, all we can do is just rearrange this equation and say nabla U is equal to F minus I. So if I know F, I can easily find nabla U. Because if we look here, we can say that nabla U is equal to F, which is the partial derivatives of x1, x2, and x3 with respect to big X, big X1, big X2, big X3, which again, we know this was part A. And all we have to do is subtract the identity matrix. Well, Clayton, what exactly does this look like? Well, if we look at the matrix on the very right, we can see that all we're doing is we're taking those diagonal components and subtracting 1 from each one of them. So if I know F, all I have to do is subtract 1 from each one of the diagonal components, and I'll be given nabla U. So again, if we know F, to find nabla U, it's very, very simple. We don't have to do all that work that we just mentioned in the previous slide. All we have to do is subtract 1 from all the diagonal components. So now after we determine the two gradients, we can start looking at some of the characteristics of the deformation. So remember that we were able to determine if the deformation was physically possible through the determinants of the deformation gradient F. So here's kind of the key here. F is going to be what we're going to use a lot. Nabla U does have deformation characteristics. I'm not saying it doesn't, but F is a very nice, easy way to determine those characteristics. So this is why we picked the deformation gradient F rather than nabla U. Because if you guys remember, we were able to say, okay, well, if the determinant of F is greater than 0, the motion will be, or the deformation will be physically possible. Now, if the deformation gradient in F is less than or equal to 0, we say that this is physically impossible. And again, we talked about this in question number 2, where we were saying, well, if the determinant of F is negative, this means that the volume after deformation is negative, and that just makes no sense. But now we're going to ask ourselves, well, if the determinant of F is so powerful and it's able to determine if something is physically possible or impossible, well, what else can the determinant of F tell us? Well, recall that the determinant of the deformation gradient is related to the ratio of an object's volume before and after deformation. So therefore, we can say, well, if the determinant of F is greater than 1, this means that our final volume is greater than our initial volume. So therefore, our volume of our object is actually expanding. Now, if our determinant of F is less than 1, this means that our final volume is less than our initial volume. So therefore, the volume is contracting, it's shrinking. However, if our determinant of F is equal to 1, this means that there's no change in volume. Our final volume is equal to our initial volume. So now we're starting to see that we can do two things with the determinant. The first one is compare it to the value of 0, because this will tell us if something is physically possible or impossible. And then the next thing that we do is we compare it to the value of 1. And this will tell us if our volume is expanding, contracting, or if there's no change in volume. So this right here will give you the answer to part D. And with that, that concludes actually question 3. But I just want to leave you guys on a note with this. That determinant of F tells us a lot about the deformation. This is why it's so important in continuum mechanics. I know a lot of students, when we go through weeks 1 and week 2, and we're just saying, well, this is just linear algebra. This means nothing. It's physically meaningless. But now you guys can see the power of a determinant. It can tell us a lot about actual deformation in real life. And once we start talking about strains and stuff like that, you guys will physically be able to see it, how an object starts getting stretched, how it gets compressed, stuff like that. So hopefully this kind of shows you guys why we do all that linear algebra review. I hope you guys know that it's not meaningless in a sense. So again, that concludes question number 3. Thank you guys so much for listening. I will see you guys in question number 4.